Hello, everybody. I'm Lucas Campos, and today I'll be introducing the Physics 2211 Lab 5 Choose Your Own Adventure following Slinky. In today's agenda, we're going to start off by looking over at the introduction and purpose of the lab, the fundamental principles, going into the tracker, to the glow script code, going into possible errors, and finishing off with a discussion question. All right, moving into the introduction and purpose of the lab. In this lab, we're analyzing and predicting the motion of a falling Slinky that's dropped from rest, and we're going to see the influence of gravity and drag on that motion. And then we use Tracker to plot the movement, and then GlowScript to create a computational model for that same situation. And our initial conditions is the Slinky mass is roughly 0.21 kilograms, and we're starting out from rest, so 0. Moving into the fundamental principles used in this lab, we start off with Newton's second law, and here we have the velocity update formula. Vf equals Vi plus F over m times delta t time. And then we have F net equals the change in momentum over the change in time. And we have gravitation force, which is just negative mg in the y direction. And spring force, negative k L minus L naught times L hat. Moving into the tracker, here I put in the video of the Slinky falling, and I plotted the center of mass of the Slinky, the bottom of it. And basically in the video, the Slinky starts up here and it's kind of hanging and it drops. And as it's dropping, the top is moving. However, the bottom point is staying stationary. And then as the top moves down, the bottom is still stationary until the top hits the bottom, and then the bottom starts to move. And I'll talk about this more later, but that can be represented in the graph where we see it's basically it's motionless. The bottom of it's motionless and stationary along the x-axis until the top hits it, and then it eventually turns into a downward slope. You have the glow script model to compute the computational side of this experiment. And here we had to change a few things. So the system 0.21. The velocity vector is just 0 because it's starting from rest. And then we change the delta, the time of each timestamp, because it's such a fast-paced video that we really want to slow it down and see the points graphed more. And then over here we have two sides of it. There's two parts of it while it's stationary, and then once the top hits the bottom, it starts to move. So there's two different time intervals. And here we have the ball, for example, the ball velocity plus F net over m times delta time. Is the ball position is equal to the ball position plus the ball velocity times delta times change in time. And then over here we have the second time interval, and we have F net is the work plus FD, and then FD is like the force of drag. So U times negative B times the magnitude of the ball velocity squared times normal force of the ball velocity. And then we get the that the ball velocity is equal to the ball velocity plus F net over m times delta tat. So it's a little bit different here because in this situation we have drag force. So at first we don't, and then we do. So it's different. And using the tracker and glow script, we have some graphs that will result from it. So here's the graph that was shown earlier from the tracker. So we see that here it's 0 until the top hits the bottom, and then it starts to move down. And then the same thing happens here over in the glow script computational model. It remains at 0, and then once it hits it moves down. And then we can go in and compare these two, and we see here that they basically line up, and that the tracker is just a little bit below the glow scripts. And like I just said, that the tracker is a little bit below the glow script. That's for a couple of reasons. So possible errors is the tracker application. It's still a program that doesn't really account for outside factors such as wind influence and human error. Ending it off on the further question, does the bottom of your model Slinky stay stationary just like in the video? I said yes, because the y forces cancel out. So the force of gravity and force of tension essentially cancel out until they come down and hit each other, and then they start to move. That about wraps up my presentation. So thank you for listening.